Hi, I'm Ashim Datta, professor in the Department of Biological and Environmental Engineering at Cornell University. This short module is in a series intended to help recap the math that might have been done a year or two earlier before taking an undergraduate course on heat conduction or mass diffusion. This particular module is to help solve the 1D heat equation or 1D diffusion equation in cylindrical coordinate with value given boundary condition. In 1D cylindrical 1D cylindrical coordinate, the heat equation or the diffusion equation is this 1 over r del r of r del t del r, where t is the dependent variable and r is the independent variable, is equal to 0, or del r of r del t del r is equal to 0. Notice that t is a function of just one variable r, so we can also write ddr of r dt dr is equal to 0. Now, because this r is inside, this equation in the cylindrical coordinate is obviously not the same as the 1D Cartesian equation, which is d square t dx square is equal to 0. So it's not the same, because if I expand this, then what do I get? R d square t dr square plus dt dr is equal to 0. So that equation is obviously very different from this one. Okay, so our techniques would obviously have to be different. So the trick to solve this is not to expand, not to do this expansion of the term. So instead of doing that, I will start from d dr of r dt dr is equal to 0. So that gives me r dt dr is equal to some constant, and so dt dr is equal to c1 over r plus c2. So t is equal to c1 integral 1 over r dr, plus c2. It's when we integrate, then we get the constant of integration, is equal to c1 natural log of r plus c2. So now c1 and c2 are unknowns, so we get them from boundary condition. So this particular one is for using value given boundary condition. So t at r equal to r1 is, let's say, t1. So this is given. Okay, it's a value, and then t at r equal to r2 is t2, and the same. Okay, so with that we want to solve for the C1 and C2, and so plugging in the first one, plugging in BC1, so T1 is equal to C1 natural log of R1 plus C2, and plugging in the second one in BC2, T2 is equal to C1 natural log of R2 plus C2. So subtracting, I get T2 minus T1. T2 minus T1 is equal to C1 natural log of R2 minus C1 natural log of R1, which is equal to C1 natural log of R2 over R1. From this, we get C1 is equal to T2 minus T1 over natural log of R2 over R1. Now, we also need to find C2, of course. So for that, we take the solution itself, which is T equal to C1 natural log of R plus C2, and subtract that from the first equation we got from the from using the first boundary condition on the previous page, C1 ln of R1 plus C2. So if we subtract, we get T minus T1 equal to C1 natural log of R minus C1 natural log of R1, which is equal to C1 natural log of R over R1. And so what we do is we now substitute for C1 that is already known. So this is equal to T2 minus T1 over natural log of R2 over R1 times natural log of R over R1. So then my solution is T is equal to T2 minus T1 over natural log of R2 over R1, this together, times natural log of R over R1 plus T1. So this is my solution of T, the dependent variable, as a function of R. So T as a function of R. Okay, and so notice that this solution is very different from the 1D Cartesian coordinate, where the temperature solution was linear.